All right, good morning and welcome to lecture 4. Today we'll be talking about phases and phase changes and kind of bringing in some information from lecture 3 about heat and energy transfer. So I'll pull up the PowerPoint here. All right, so we'll get started. All right, so just to kind of kick it off, go ahead and try to answer this question. This is just asking kind of at a molecular level what is happening to water. So each of those little drawings that I'm point to them here. This drawing here would be a water molecule, right? 2 hydrogens and an oxygen. And so in all these squares, this represents water. And then this would be what's happening when it's boiling, okay? So you could kind of, if you look at A, I guess we'll just go through the answer here. So B is the answer, right? What's happening when water boils? So when water boils, it's still water, just in the gas form, right? And so in all these other drawings, you can see like in this first one, the H's go together, the hydrogens go together, and that's just hydrogen gas. And then you have the oxygens together, which is oxygen gas. And so what this is showing and what we know is that water doesn't actually change. The molecule doesn't change itself. The molecules just spread further apart when water becomes steam, right? When it boils. So this will lead us to talk a little bit about the difference between a physical change and a chemical change. Okay. So in a physical change, the properties might change. So for example, with water, it goes from a liquid to a gas. That is a change. But since the molecule itself doesn't change, this is just a physical change, okay? Okay, so again, just to kind of recap physical changes here. The identity and composition of the substance do not change. So if you have water molecules in ice, for example, you freeze water, you still have water molecules in there. They're just arrayed in a more like crystalline structure. And then when it turns into water vapor or steam, the molecules are just much further apart than they were when they were a liquid, okay? So the state can change, solid, liquid to gas, or you can break the material into smaller pieces, okay? So anytime that the molecule itself just doesn't change, that's a physical change, right? If something is happening. Chemical changes are when the molecules themselves actually do change, right? So in this example, you have these iron nails, and when they rust, the iron combines with oxygen to make a new molecule, which is iron oxide, okay? So you go from iron to iron oxide. So this is actually a chemical change because you now have a new molecule that's being formed when rust forms, okay? So during a chemical change, substances react to form new compounds with different compositions and properties. Oh, sorry. And this would be a chemical reaction taking place, okay? So if we look at changes of state or phase change, let's see. Sorry, I got a bunch of pop-ups here. Okay, should be good. All right, so this summarizes the phase changes here, okay? Okay, so the snowman here represents solid, okay? So this would be like ice. And then the puddle of the snowman, right, would be liquid. And then you got gas up here, okay? So moving from solid to a liquid, right, melting, Most people are familiar with that word. Liquid back to solid is freezing. From a liquid to a gas. If it's water, we generally call it like boiling, right? But the technical term would be vaporization because it's turning into a vapor. And then from gas down to liquid is condensation. You probably see that like in the mornings in your cars, you see condensation, right? And then from the gas to the solid, we don't see very much, so you might not be as familiar with these terms. We have deposition, when it goes from gas to a solid, and then sublimation from a solid to a gas. So just be familiar with these terms, and if you're not familiar with any like process that goes between solid and gas, if you've ever seen dry ice, if you just leave it out, the dry ice will slowly evaporate, but it never actually goes through a liquid phase, right? It goes straight from a solid to a gas. So dry ice is frozen carbon dioxide, and just under atmospheric normal conditions, it's just going to go straight to a gas if it's left out. Okay. All right, so go ahead and try this quiz, and go ahead, you can pause the video. All right, so go ahead and answer this. So in this quiz, the question says, what is the final temperature of water if we add 10 calories of heat to 1 gram of water that is currently at 100 degrees Celsius? Okay, so walking through what we did last time. Okay, so we have Q equals MCAT, right? This is our equation we learned from the last lecture. So Q we know is 10 cals, right? 10 calories. So 10 calories for our Q unit. Mass would be 1 gram. Okay, that's the mass. And then we have our specific heat of water, which is 1.0 calories per gram degrees Celsius. And then we can solve for delta T, right? Because we're looking for the final temperature. So let's solve for delta T here. So delta T just equals 10, or yeah, 10, right? So we have 10 divided by 1 times 1, which is 10. So delta T equals 10 degrees Celsius. So if the water is starting at 100 degrees, right, we would imagine by adding 10 calories of heat, it should go up 10 degrees Celsius, right? So let's look at the answer, and it might surprise you what we got, but we'll talk about why here in a second. So the answer to this question is actually 100 degrees Celsius. Okay, so why didn't it get hotter, right? We're saying it actually stayed the same, okay? So at 100 degrees Celsius, that's the point at which water boils, okay? And so even though you're adding more heat, right, the water boils off. The temperature remains at 100 degrees of the water. The energy that's added actually goes into changing the phase. So we're going to talk about this, and I'll show some diagrams that might help illustrate this principle. Okay, so there's no temperature change while the phase is changing from like a liquid to a gas or a solid to a liquid, okay? The heat that you add is the energy that's being required to melt or boil it. It doesn't actually change the temperature. So maybe search YouTube if you want for this demo. You don't have to, but basically what I usually do is have a mixture of water and ethanol, and you dip a dollar bill in it, and then you light the dollar bill on fire, right? And what happens is there's a big flame around the dollar bill, and the dollar bill doesn't actually burn, okay? So what's happening is, so paper burns at 232 degrees Celsius, and water boils at 100 degrees Celsius. So when you light that dollar bill, you're actually, the flammable part is the ethanol that's also mixed in with the water. So the ethanol lights on fire, and all the heat from that ethanol flame heats up the water to 100 degrees Celsius. But the water never actually gets hotter than that, right? And so the dollar bill never gets hotter than 100 degrees Celsius. And since it burns at 232 degrees Celsius, the dollar bill never burns. Okay. So all the energy that's added converts the water into steam, but the water itself never actually changes temperature. Okay. So the heating curve, I think, is the best way to illustrate this. So if you look at this curve, what this is, we have heat added, or energy, on the x-axis here, and then on the y-axis we have the temperature. Okay. So if you take, for example, let's start here on the curve. As you add energy, so as we move to the right, the temperature goes up, okay, until we hit the melting point. So let's say this is water. This would be 0 degrees Celsius, okay? Once you hit 0 degrees Celsius, you continue to add heat, and the temperature does not change for a while. All that heat is actually going into the solid to spread the molecules apart, or break them apart from their the bonds that are holding those molecules together. And once you've reached that certain amount of energy that's required to do that, then it transforms into a liquid. And then once we're in the liquid phase, as we continue to add heat, the temperature rises, right? Just like we would normally think. Then you get to the boiling point, which for water is 100 degrees Celsius. And at that point, you're adding a bunch of energy in, right? Moving to the right, and the temperature doesn't change because all that energy is being used to spread those molecules even further apart to turn it into a gas. And once it becomes a gas, as you continue to add heat, or energy, the temperature will rise after that point. So you have all these different zones here, okay, that we're going to look at. So in the problems that we dealt with in the last lecture, we just looked at transitions between, like in between the different boiling points and melting points. So if we looked at like when we're adding heat to water and stuff like that, we always kept the water in between 0 and 100 degrees. So you were only seeing this little picture, right? So the little analogy I like to use when I'm talking about this, it's kind of like dating my wife. So we started dating, right? I added some energy, I was putting forth a little effort, and things are moving along. Then it kind of gets to this point where you're like, are we gonna like take it to the next level? Like, are we gonna start like really dating, right? You're adding this energy, nothing's really happening. But then finally she said, yeah, we could be boyfriend, girlfriend. So we start moving up this ladder, right? And we're adding energy. And we get to this point where it's like, do you want to get married, right? So then again, it's like, I'm all for it. So I'm adding all this energy and she's putting on the brakes. So we're not really moving. And then finally she says, well, she actually dumped me for a second. So we come down here, dump me, come back. And then we move on to get married. So anyway, I don't know if that helps or not. Just something I think about when I see these heating curves. All right. Cooling curve is the same thing, just walking down the ladder, okay? So it's the same thing. You start with a gas, and that as it releases energy, the temperature doesn't really change. The release of energy is just allowing the the steam to convert into water. And then as you pull energy out, right, this is heat removed, the temperature goes down, and you follow a similar line just on the way down, the reverse of it. All right, so sketch a heating curve for aluminum, okay? This gives you the melting point and the boiling point of aluminum. So go ahead and try and do this real quick. All right. Go ahead and draw one out. So this doesn't need to be super specific because we obviously don't know that many properties, but we just know that heating curves look like this. Oh, that should be a flat line, and up, right? And then all you know is the melting temperature, which is 660 degrees Celsius, and the boiling temperature, which is 2,470 degrees Celsius, right? Okay, so probably should have made this line a little bigger because that's a big jump in temperature, but whatever. That's really hot. 4,500 degrees Fahrenheit to boil aluminum. Can you imagine aluminum gas? That'd be crazy. Okay. So now we move into some of the calculations, case, because we did that question, right? And it wasn't, I'm assuming when we talked about the question about adding heat to water at 100 degrees, I think a lot of people probably thought the temperature would go up, right? So we're going to talk about how to calculate what happens at that point. So, for example, how much heat is required to melt a 15-gram ice cube? Okay, so if we look at like the heating curves that we did, right? So this part right here is the transition between solid and liquid. So there's a certain amount of heat that we actually have to add in order to jump it from the liquid over to the solid diagonal, right? Or going the other way, you could say if you're coming down here, you're up in the gas region, you want to go from steam to liquid, right? That's condensing. How much heat needs to be released? So how much heat along this line needs to be released to make the jump from a gas down to a liquid, okay? So we're definitely going to need more information. So this is the second equation that you'll want to know for heat calculations. The first equation was Q equals MCAT, right? Okay, so that's the first equation. And then this is going to be our second equation. So heat of fusion, delta H, is going to stand for either the heat of fusion or the heat of vaporization, okay, these two values. So heat of fusion is between solid and liquid, right? Solid and liquid. So either it's when ice melts or it's when ice forms, right? You're going between the solid and the liquid phase. Heat of vaporization would be turning things into a vapor, right? So you're going from the liquid to the gas phase, okay? Or from the gas to the liquid phase. Either way, this is the same number. And then you have the heat of sublimation, which goes between solid and gas, right? If you remember that phase chart we looked at. So between solid to gas or gas to solid, you're going to be looking at the heat of sublimation, okay? All right. Okay, so where do these fit in on our curve? So on all the flat lines, we use Q equals M delta H, okay? And for this flat line, specifically, we use Q equals M delta H fusion, right? The heat of vaporization of fusion, because we're transitioning between the solid and the liquid. This one, again, a flat line, horizontal line. We're going to use Q equals M delta H, but in this one, it's Q equals M delta H vaporization, okay? Vaporization, again, is the transition between the liquid and the gas phase. And then for the liquid, we have Q equals MCAT. We already talked about that one. So any of the diagonal lines, just use the same equation that we already talked about. So now, I mean, we can do problems where we actually start anywhere on this line and go to another place on the line. So, for example, let's say we start here at this red dot, or sorry, you'd actually start at this part, sorry. Okay, and then we want to see how much energy is required to bring the, at this point it's a solid, how much energy is required to take that solid to a gas at 120 degrees Celsius, okay? 120 degrees Celsius. Right now this is at 0 degrees Celsius, okay? So we have a horizontal line here, okay? So that means we're gonna have, I usually write like Q1, okay? That's your heat right here, Q1, plus you have whatever heat takes you along this diagonal, right? So the amount of heat we need to get it up to this point is gonna be Q2. Then you have a Q3, which brings you along this horizontal line, okay? Oh, sorry, Q2. Q3, right, is going to be the amount of heat to convert something from a liquid over to a gas. And so now we came up this, we go across horizontal. And then finally, right, this is at 100 degrees Celsius. So we have the Q4, which takes us from 100 degrees up to 120 degrees Celsius in the gas phase. That's going to be Q4. And since Q4 is on a diagonal, that's going to be the MCAT equation, okay? All right. So you may not have a lot of problems that require you to do 4 heat calculations and then bring them and then add them together. But you can see that you could really do, I think 5 is the total possible that you would need to do. But let's look at some practice problems. So how much heat is required to melt a 15-gram ice cube? Okay, so if the question is just asking to melt an ice cube, we look at the heating curve, and I recommend, you know, if you're struggling with the concept, draw these heating curves out just like this. Nothing fancy, right? For each problem that you're doing. So if it says how much heat is required to melt a 15-gram ice cube, saying what that is just saying is how much heat is required to transition from solid to liquid, right? So that transition is going to be this horizontal line right here, right? And if you remember, horizontal lines use the Q equals M delta H equation. So here we're just going to say Q equals M, which is 80 calories per gram, right? Times, oh, sorry, that's not M, that's delta H, right? We can flip-flop these. Q equals delta H times M, right? So delta H times M, which is 15 grams, gives you your answer, right? So that would be 1,200, I think. 1,200 grams, accurate to 2 sig figs, which we are here, so we're good. Okay, so that's just walking through it. Yeah, oh, sorry, not grams. 1,200 calories, right? Clear my drawing off. Okay, so 1,200 calories, and then if the answer wanted it, you could put it into 12 kcals. And the important thing is absorbed, right? You could have transition from from a liquid down to a solid, and in that case, you're actually releasing energy, okay? So just kind of, you can kind of just think of ice, right? If you add energy to ice, it turns into a liquid. So in this one, we're melting ice cubes, right? So that is going to be absorbing heat, right? We're putting heat into it. How much heat is released when 5 grams of steam condenses? So for this, you could draw a cooling curve. So if you drew the cooling curve, it'd be something like this. I think it's honestly easier just to remember one curve. Sorry, still haven't figured out how to clear these. So what I usually do is just draw a heating curve for all of them, and then I just move backwards. So here's my very rough heating curve. Sorry, that's not good. Okay, try again. A little better here. All right. All right, so we're going from 5 grams of steam and we're condensing, right? So we're jumping from this point over to this point, right? To this liquid phase. Okay. So the second horizontal line uses the heat of vaporization, right? So again, with these horizontal lines, we're using Q equals M delta H. So we can say Q equals 5.0 grams times 540 calories per gram. Okay. All right. And you multiply those together, Q is going to equal 2,700 calories, right? Okay, and so that's how many calories is released, right? So depending on what the question's asking, it could say how much heat is released, or it could just say how much heat is transferred or something like that. But you may see a negative number here. So sometimes you'll see this as negative 2,700 calories, which is just denoting that the energy is being released. But it would be also okay to say 2,700 calories were released, right? Or you could say negative 2,700 calories were transferred or something like that. So just pay attention to kind of the verbiage there. Okay, so here we use a positive number, but we say it's released, right? Okay. All right. So go ahead and pause the video and try this question. All right, let's work through it. So how much heat is released when 25 grams of water vapor is deposited onto your windshield as ice, right? So this one we're going from a vapor down to a solid, right? So gas to solid. So that's that sublimation change that's happening. So it's not really easy to see on a heating curve, but it's the same idea that we've talked about. So because we're doing just a phase change, temperature is not really changing, we're just going from vapor down to ice, we're going to use the M delta H. And for this one, we're using the sublimation because that's that process between solid and gases, right? Okay, so Q is going to equal 25 grams times 620 calories per gram, right? So run the math out on that one. About 15,500 calories. If you convert it to kcals and then round it to two significant figures, you're going to get E. Okay. All right, more examples. This is good practice. So now we have an ice cube that's at 0 degrees and it's heated until it melts. Okay. The water continues to be heated until it all boils away. How much heat was required? So easiest thing to do for these ones, all right, you look at your heating curve. Okay, again, this is what you're going to want to draw for a lot of these. We have a 25 gram ice cube at 0 degrees. Okay, so that's going to be right here. It's at the ice side of this horizontal line. Heated until it melts, so it goes along this line here. The water continues to be heated until it all boils away. So this is right here is the point at which it boils away, right? So we heat it up to this point, continue adding energy until it's all boiled off, okay? So that means we're gonna have a Q1, we're gonna have a Q2 for the horizontal, and we're gonna have a Q2 for the diagonal, and a Q3 for the horizontal. So Q1 is horizontal, so that's gonna be M delta H, okay, and that's of fusion, because that's the bottom line there. Q2 is a diagonal, so we're going to be using the M cat. Q equals M cat, right? And then Q3 is a horizontal line, the second one, so that's M delta H of vaporization, right? Cool. Okay, here we go. So if we do this first calculation, Q1 equals the mass, which is 25 grams, times the heat of fusion, which is 80 calories per gram, okay? Q2 is going to be the mass, which is 25 grams, times the specific heat of water, which is 1.0 calories, calories per gram degree Celsius. And then we have delta T. So if we're going from the melting point up to the boiling point, that would be 100 degrees Celsius, right? We're going from 0 to 100 degrees Celsius, so that's a change of 100 degrees Celsius. And then we have Q3, which is 25 grams times the heat of vaporization, which is 540 calories per gram. Okay, so you're gonna run through all these, get an answer, and then add them together for your final answer here, okay? So let's walk through it with the slides here. Okay, again, so you get your Q1 there first on the horizontal line. Q2 is Q2 is equal to MCAT for the diagonal. And then you have your third horizontal line, the transition from liquid to the gas. So it's going to run through all the calculations, okay, that we already set up. And then you add them all together to get a total of 18 kcals, okay? So a lot of these problems, you see that you convert from calories to kcals. Again, it's just going to depend on what your answer choices are for the problem. But it's easier to look at it in terms of kcals generally because these can be large numbers. Okay. All right, more practice problems. So hopefully you've kind of understood the concept by now and you can apply these in different ways. So this quiz is a little, let's see, probably a little trickier. Go ahead and try it, pause the video. Okay. So again, if you're following along on YouTube and stuff, I encourage you to pause the video and try, see as far as you can get. If you get stuck, then you can play the video for a little bit until you get unstuck, pause it again and keep going, right? See how much you can do on your own. I think that'll really help you guys as you get ready for the tests and stuff. Okay, so we have a 50-gram cube of ice. So when I read these questions, I like, especially long ones like this. I guess it's only three sentences. No, 2 sentences. Anyway, not super long for a chemist. So I like to kind of draw things as I go along. Okay, so I have a cube of ice, okay, 50 grams. There we go. All right, 50-gram ice cube at 0 degrees Celsius, okay? And it's placed on a 500-gram block, aluminum block. So we put it on an aluminum block, that's 500 grams. And this is at 50 degrees Celsius. What is the final temperature of the aluminum as soon as all the ice is melted? Okay. So first we need to figure out, so this ice is going to be converted into liquid, right? So we're going into liquid. For ice to be converted into liquid, it needs to be taking energy, right? So there's going to be energy flowing from the aluminum into the ice cube, right? Because this is at 50 degrees Celsius. So that's, you know, hotter than like 100, it's probably like 150 degrees Fahrenheit, is my guess. I can't do these quick in my head, but it's hot, right? Okay, so the energy from the aluminum is going into the ice cube in order to melt it into a liquid. Okay, and so we know that we're assuming this transfer of energy is perfect, okay? So the energy that leaves the aluminum is the same as the energy that goes into the ice cube. So in order to know how much energy leaves the aluminum, right? The aluminum is not changing phases, okay? It's staying as a solid. So if we look at the Q of the aluminum, redraw that. Q of the aluminum, right? That's going to be MCAT. Okay. So we know what the mass of the aluminum is. We know what the specific heat of the aluminum is. But we don't know what the final temperature of the aluminum is. So this is kind of an unknown variable. We also don't know how much heat leaves the aluminum from the problem. It doesn't just state it outright. So we can't really figure this out on its own. In order to figure it out, we need to know how much heat actually leaves the aluminum. Then we can solve for the change in temperature, which is what the question's actually asking, right? The final temperature of the aluminum. Well, we need to know Q, M, and C in order to figure that out. So we know that the amount of heat that leaves the aluminum is going to be equal to the amount of heat that enters into the water, okay? And so ice, okay? So the ice is at 0 degrees and it's just transitioning over to a liquid as soon as all the ice is melted. So for the ice, if you drew a quick heating curve, really we're just talking about this horizontal line right here, right? It's going from an ice cube to a liquid, but it doesn't mention the temperature changing at all. So the Q for the water, since it's on the horizontal line, this is going to be M delta H of fusion, right? Okay. So we have the mass of the water, or the ice cube. I say H2O, but it's ice cube. 50 grams, right? Times the heat of fusion for water, which is 80 calories per gram. Okay, so you have 50 times 80. So that would be, what, 4,000? 4,000 calories, right? If we converted that, well, we'll leave it in calories for now. Okay, 2 sig figs, right? So technically this should be 4.0 times 10 to the third calories, okay? So that's the amount of energy that goes into the ice cube to melt all the ice into liquid. So now we know what Q of water is, right? So we know this number. The heat from the water is equal to the heat from the aluminum. So we can rewrite this equation as, well, let's start it here. So you have heat from aluminum, again, is MC delta T. Okay, so then we know the heat that's leaving the aluminum is 4.0 times 10 to the third calories. We know the mass of the aluminum is 500 grams. Specific heat of aluminum is 0.215 calories per gram degrees Celsius. And we're solving for delta T, okay? So we'll go through all these calculations. Algebra, you'll solve for delta T, which tells you the change in temperature of the aluminum. So then whatever the change is, you'll just subtract it from 50 degrees to get the final temperature. So walk through it here. So we have the Q melting of the ice cube, right, equal to 4,000 calories, like we talked about. And then the Q removed from the aluminum, we're going to use Q equals MCAT, okay, and solve for delta T. So you've got the heat removed over the mass, which is 500 grams, also divided by the specific heat. This is just the equation right here rearranged to solve for delta T. Okay, and we get delta T equals 37.2 degrees Celsius. So that's how much the temperature changed. That's not the final temperature. To get the final temperature, you then take your initial temperature that you had, subtract it by the change, right? It went down because it was releasing heat into the ice cube. to get your final temperature, which is 12.7 degrees Celsius. Okay. So that's kind of a multi-step problem. Those can be hard to know what to do when you just look at it initially. But if you're on a test or homework, just start drawing things and writing things that you know. By doing that, you identify the stuff that you don't know, right? So, for example, for this question, kind of like I showed you, the question was asking, what is the final temperature of aluminum as soon as all the ice is melted? Well, I'm thinking, okay, we can use Q equals MCAT to figure that out. But once I wrote that out, I realized, I don't know how much heat left aluminum. So then you got to go back into the problem and say, okay, we can figure that out using the ice cube, right? And start pulling information you need. So drawing stuff, writing out equations, writing out what you know, maybe like a list. These are the things I know. These are what I need to solve, right? Stuff like that. Just move forward, okay? A lot of people hit these problems and they just stop because they say, I've never seen a problem like this. Well, that's kind of what chemistry is all about, right? It's all about seeing new problems and learning how to walk through them step by step and figure it out, okay? And that's what we're trying to teach in this class. All right, so just for the last slide here, these are just some definitions that could be useful. I'm not going to go over them. It's kind of boring just to talk about definitions because I'm just reading you a definition. But you can look these up in your book and just kind of know what they are. All right, I think that's it for this lecture. Hopefully things are going well in the class, and stay up to date on homework, stay up to date on watching your lectures, and check the schedule for when the exams are. And really, organization is going to be very important because this class moves quite fast. So, all right, we'll see you next time.